Salam and welcome everyone. So today we're going to be working on the question on the screen that says estimate the internal pressure of water vapor at 1.00 bar and 400 kelvins, treating it as a van der Waals gas when the internal pressure is equal to A divided by Vm squared by assuming that the molar volume can be predicted from the perfect gas equation. So as this question has a lot of words. As you can see, it's not a hard question. First of all, we're blessed with the fact that the equation that we're supposed to use to solve this question is already given to us, right? This here, this VM right here represents molar volume, okay? For all of you who may need a little bit of a review. And this A right here simply represents the strength of attractive forces. So basically, we're dealing with the real gas here. But they told us that in order for us to determine the molar volume, we can use the perfect gas equation in order for us to simplify the problem. Meaning, even though it's a real gas, we're going to be using the ideal gas equation just to determine the molar volume. So what that looks like is for us to remember that Vm, okay, is the same thing as RT divided by P, right? Remember, PV equals nRT. Vn is the same thing as V divided by number of moles. So if you divide by number of moles and P on both sides, what you end up with is going to be Vm equals RT. So this is the equation that we're going to use to find the molar volume of the gas. Next, the best thing for us to do in order for us to continue this work is for us to determine the attractive forces value, which is A. Well, thankfully, this is a constant. So all you have to do is to look at the resource section of your book or go online and Google the A value or the attractive forces or strength of attractive forces value for water vapor, and it is a constant. And since it wasn't given to us, please go online, Google it, or just look at the resource section of your physical chemistry textbook. And looking at the textbook, what I have is 5.464 dm6, okay, atm divided by mole squared. So having this information is very, very key. Now, we're also told, right, that the temperature is 400 kelvins and the pressure is 1 bar. But we have strength of attractive forces constant to be in ATM. So what this is telling you is that we have to go from bar, okay, to ATM. So if you're new to this channel, I've done unit conversion questions on for pressure. So if you want to learn how to do that in a more intense level, please watch that video. But I'm going to be doing that here just briefly. So we know that 1 ATM, okay, is actually equals to 1.01325 bar. Okay. Hence, 1 bar is going to be equal to how many pressure. So all we have to do is just simply cross multiply. So what we end up with is, I'm going to be doing it right here. Let's continue here. There is space here. What we end up with one is 1.01325 bar. Okay. P, and remember, we're cross multiplying is the same thing as 1 atmosphere bar. Okay. Of course, since we have same units on both sides of the equation, we can cancel this out and we have actually pressure to now equal 1 atm, okay, divided by 1.01325. And when we do that, we determine pressure to be 1 divided by 1.0325 bar in our calculator. We end up getting 0.97402 atmosphere. So that's basically the pressure we're going to be using. So we know the pressure, okay? Knowing the pressure and also knowing the temperature that we're given, as well as knowing the gas constant, which is a constant, we can successfully determine the molar volume. So solving for the molar volume, we have RT divided by P. We know that R is just basically gas constant, so that's 0.08206 dm cubed ATM divided by mole Kelvin, okay, times 400 Kelvin divided by 0.97402 atmospheres. So we're going to cancel out the atmosphere, cancel out the kelvins. So what we end up with is the molar volume is going to give you 0.08206 times 400 divided by 0.97402. And that, of course, is going to have the units dm cube per mole. So we're going to put that in our calculator to get 33.6995 dm cubed per mole. So that's basically how you do it. Now let's go back to the question. We've been given the formula we're supposed to use for to determine we've given the formula that we're supposed to use in order for us to determine internal pressure. So we're just going to rewrite that here. We have internal pressure, okay, equals A divided by Vm squared. So internal pressure would look like this. A is just simply 5.464. Okay, looking back at what I showed you here. So A is 5.464 dm6 atm divided by mole squared. So dm6 or yeah, dm6 atm divided by mole squared. All of that information divided by 33.6995 dm cubed divided by mole, all squared. So, of course, we go on to do the math. So we have 5.464 dm6 atm, okay, divided by mole squared, divided by 33.6995 dm cubed, divided by mole, all squared, is going to give you 1135.6563 dm6, okay, divided by mole squared. So basically that squared was there for us in order for us to properly cancel out the units and retain the unit of pressure, since we're just determining internal pressure. So dm6 cancels out, dm6 cancel out, mole square cancel out, mole squares cancel out. So 5.464 atm divided by 1135.6563 would give you the internal pressure of 0.0048113 atm. And of course, this is our answer. But the thing about chemistry is that we have to put things in the proper number of significant figures or decimal places. We see that we're given this question of bar in three sig figs, 300. I'm sorry. We see that we're given the pressure 1.00 bar in three sig figs and the temperature in 400 kelvins, which is also three sig figs. That means we have to put our answer in three sig figs. So really, the internal pressure, the answer for it is just simply 0.00481 atmospheres. So that is basically how you solve this question. So yeah, that's basically how it's done. If you have any questions, please put in the comment section. If you would want personalized tutoring, I am a tutor that helps students in high school, middle school, and college succeed in their STEM related courses as well as in other aspects of their academic career. So if you like help in your class that you're struggling with, whether it's tutoring or mentorship, please email me at shohabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.